So an important functionality of the NanoFraser is the reading functionality. So usually when we work in the closed loop operation, we have both a writing and the reading process, but we can also just make use of the reading process. So when we are in the warm-up, if we select the reading layout or reading arbitrary, usually the most used is reading arbitrary, we can just make use of the reading functionality. So how does this work? Well, first of all, we can make an arbitrary area. We can design this rectangle as much as we want, as large, as thin as we want. If we want to have more control over the position, we can change the rotation, the size, and the pixel size, for example. This is already quite an interesting thing that we can adjust directly from here. So let's say we want a pixel size of 30, never mind, so 30 nanometers. Now we are outside the piezo range, so we need to allow the stage movement in order to do this reading. So we can move our reading area wherever we want. We see that we have the scan region and the reading region. We don't have any writing region here, and we don't heat up the writer, of course, when we do just the reading. We just use the topography sensor in contact mode, measuring the topography of this step in this case. In the settings of the warm-up, you see that we can also change again the coordinate system, so we can use either the warm-up or the piezo center. Piezo center is, in this case, around here, so at the center of the tip location, and we can also change the aspect ratio and the margin on X and Y. In this case, it's 1 and 0.5. We can do 1 and 1, for example. So once we are happy with the location of our reading area, we can move toward CLL. In this case, you see that all these parameters that are related to the, let's say, the writing are grayed out. So the temperature and the force is grayed out, but we can change some reading parameters such as the read height. This is important parameters to change when we're reading, because we basically tell the NanoFraser how deep we can go looking for our surface in case we have a step, for example. Here it's clearly we have a pattern that can go down to 100 nanometers, for example, because we blasted with the laser. So in this case, the NanoFraser will go down to around 15 nanometers in depth looking for the surface. If it doesn't find anything, it will not find contact, so we will read out of contact and we will have basically an artifact, a huge artifact. All this area will be an artifact. So to make sure that we read the bottom of our arrow, we can select, we can put as a scan height something that's like 120, for example. So we make sure to read all these depth. An important thing that we also need to take into account when doing reading, but in general also when doing writing, is flattening. So when we use the NanoFraser software, we either flatten on the right or on the left. By default, we flatten on the right. So here we see that the right is this area. So this arrow shows us the direction of scanning, so fast scan direction. And this is the left margin, this is the right margin. So we see that the flattening on the right for us, it's not really ideal because we are in the bottom of this trench. So we should flatten on the left, because this is the zero reference margin. So we can go to the CLL pattern parameters and select as reference margin on the left. We could also put the reference margin on the right and then select the depth of the reference margin, but in this case it's more simple to just put left and start the reading, because we don't know really the height or at least the depth of this margin. So we press play and we wait. So after doing, of course, the IV calibration and the approach and the trajectory management, now we're finally reading, and we see that we have quite a large depth of patterning here. We are probably not really precisely reading the bottom of our pattern, because we're going down to maybe more than 120. So to make sure that we actually read all of the trench, we can also increase more the scan height. We can put minus 150 and play it again, because let's not forget that we're dealing with a piece of silicon with 10% PPA solutions being coated at 4K, which usually leads to a thickness of 180 nanometers. So we can have a very deep arrow written with a laser, so it can go up to around 180 nanometers. So now we see again that with increasing the height, the profile here looks a little bit better, and we're probably reading more accurately our surface, and we actually see that we're going down to 140, almost to 160. So to make sure, we could even set a deeper reading height. So this is just to show you that also this parameter is quite important when we do any reading of a topography that we pattern, or also of a topographies that are existing on the surface. Let's see what happens if we do not really put a realistic scan height. Let's say we leave the minus 15, which is a preset value. We will not be able to read this depth, and so we will be quite far away from the real value of the depth of this step. Also, we can see from this reading that we have this sort of pile up, which is quite common when writing with the laser. You will not see when writing with the SPL, because the laser moves as a bigger spot and moves around more material with respect to the laser, so it's definitely more visible with the laser. So we see that we have a completely different topography here. We only go down pretty much to this 15-20 nanometers after crossing this pile up, so we not able to read at all the bottom of this step. So this is pretty much the most basic introduction to the use of reading arbitrary function of the nanofraser. We can also use layouts for reading. So similarly to the writing, we can import layouts and use these layouts to read. So we have a pre-imported geometry in case we have already we already know which geometries we want to read. But in general, the most common functionality is the read arbitrary, because we want to either find some flakes, some nanowires, or some other topographies on our surface, or either check the results of the laser, which is another common use case.